In chapter 1, we defined a graph as connected if for every pair of vertices in the graph, there is a path connecting those two vertices. But in chapter 2, we get a little more nuanced with what we mean by how connected a graph is. In particular, we're going to get at the idea of whether or not it's possible in a connected graph to disconnect the graph by removing a single vertex or an edge. So first, let's define what a bridge or a cut edge is in a graph. So we say that an edge E, which is, we're going to say, the edge connecting vertex U to vertex V, of a connected graph G, is going to be called a bridge, or sometimes called a cut edge, if G minus E is disconnected. In other words, if you took out just that single edge, not the endpoints, not U and V, just the edge itself, if the remaining graph is disconnected. And we have a similar definition for what it means to be a bridge on a graph that's already disconnected. We say that on a disconnected graph G, E is a bridge if E is a bridge on some component of G. In other words, if removing E from that component disconnects that component. So let's look at a couple of examples. Here we've got 5 different graphs, and we're going to try to determine whether each one has a bridge or not. Maybe it has more than one bridge. Right, so remember, what we're looking for is an edge that we could remove, which would then disconnect the graph. So in this first picture here, if I removed any part of this triangle here, the remaining graph would still be connected, right? We'd have just, if we remove this, we'd have this long path, length 4. If we removed this, it wouldn't be a path anymore, but it would still be connected. And similarly, if we removed AD, it would still be connected. But if we removed the edge BC, then the remaining graph would be disconnected, right? It would have this single component of just one vertex, and then it would have the second component of a triangle with a little tail coming off of it. So BC would be a bridge or a cut edge. Similarly, if we removed DE, this would disconnect the graph as well. So there's 2 bridges here, BC and DE. Now for H, if we removed any parts of these triangles, we could see again that the graph would be connected. But if we remove this edge in the middle, I didn't really name this, so let me just highlight it. If I remove that edge, I would be left with 2 sort of disjoint triangles, and so this edge in the center is a bridge. Okay, and in this last example here, this is a disconnected graph. So remember, to look for a bridge means to look for an edge which would disconnect its individual component. Right? There's 2 components here, 1 and 2. Here, each one of these is a bridge. If you were to delete even one of these edges, you would disconnect this graph, or this component of the graph. So all 3 of these are bridges. And in the second component here, again, those triangles, any of the edges of the triangle does not disconnect the graph if we remove them, but if we remove this here, this would disconnect that component into a triangle along with a single vertex. So all of these are bridges. 1, 2, 3, 4 bridges here. Okay, let's move on to J and L. Now, what are the bridges of J? Well, you can kind of go through and try to get a sense of it, right? There's only 1, 2, 3, 4, 5 edges here, so you could redraw the graph having deleted each individual edge and see that it's always going to remain connected. So this does not actually have any bridges. And in our last graph here called L, well, it's already disconnected, but could we remove any edge from a single component and disconnect that component? As it turns out, no, right? You can go through and just sort of try to picture in your head what happens if you take each one of these away. It's still going to end up being connected no matter which edge you take away. Similarly, if you take away any edge of a triangle, you're going to be left with a path of length 2. It's still going to be connected. So there's no bridges in this graph either. So it's worth taking a second to pause the video and think about this and try to figure out what do these graphs have in common that have bridges, and what do the graphs have in common that don't have any bridges? So you should take a minute to think about that. But hopefully we come to realize that one of the properties of these graphs down here, J and L, which don't have any bridges, is that every single edge in each one of these graphs is part of some cycle. Right? Remember, a cycle is like a closed path in a graph. So it's like a walk through a graph that doesn't repeat vertices or edges except for at the beginning and at the end. And so right in this graph, every single edge is part of at least one cycle. Similarly here, every edge is part of at least one cycle, and here as well. But up here, when we do have these bridges, each one of the bridges in each graph is not part of any cycle. And so the important thing to notice here is that each bridge is not a part of any cycle. Okay, now we saw some problems in the warm-up, or in problem 1 of the warm-up, we drew a whole bunch of graphs that all had the property that they did not have any cycles. And I just want to take a minute to define what that means. We call a tree a connected graph that has no cycles. And so we're going to see that that's actually ties in really interestingly with what it means for a graph to be connected and whether or not it has any of these bridges or cut edges. So theorem 2.1.1 formalizes this a little bit. It says that an edge E of a graph G is a bridge if and only if E does not lie on any cycle of the graph. Or another way of saying that would be an edge E is not a bridge if and only if it's part of a cycle in the graph. All right, so let's try to prove that. Let's let E, which is equal to UV, so U and V are the endpoints of this edge. Let E be an edge of the graph. And remember, it might be part of a connected graph already. G might already be connected, or G might be disconnected, in which case to be a bridge would mean that removing it will disconnect that component. So let's just assume that E is a part of the component G1 in the graph. And because the graph might be connected, that component might be the entire graph itself. It's enough for us to show that G1, that's the component that contains that edge, is connected if and only if E belongs to a cycle, right? It's essentially the contrapositive of each one of the directions of this if and only if statement, right? So we're gonna prove this statement here, that G1 minus E is connected if and only if E belongs to a cycle. Okay, so let's start off by proving the forward direction of this implication. So in other words, we're going to prove that if G1 minus E is connected, then E belongs to a cycle. This is what we're trying to prove, okay, for this first direction. All right, so we assume that G1, remember that's the component that contains the edge E. So assume G1 minus E is connected. Right, so here's our sort of larger graph G if we want to have a picture of it, and maybe it's got several components, maybe the component is just the entire graph itself. But on this component G1, if we were to remove the edge E, this is still going to be connected, okay? And so what this means is that, well, we've removed the edge E, but we haven't removed any vertices, and so U and V must still be vertices of that component. So because G1 minus E is connected, there must be a path from U to V, right? There must be a U to V path in G1 minus E. Right, you have to be able to get from U1 to V in this graph G1 where we've deleted the edge E. Okay, so let's call that path P. So maybe it's U, maybe I'll just call this U0. Oops, let's U be equal to U0. Then we have U1, U2, all the way to some UK, and that last UK is equal to V. Right, so we're just saying this is our path here, the one that's actually drawn in, that's your path from U to V. We need to show that E belongs to a cycle, right? So E, in this component, without having deleted it, E would be this edge here. And from the picture, it's pretty clear what this cycle would be. We have the following cycle, which essentially just says follow that path from U to V, and then use the edge E to go back to the beginning. We have the cycle U, which is U naught, then U1, U2, all the way to UK, which remember is just V. And then finally go back to the beginning of U, right? Because within this component G1, within your original graph, VU is an edge, right? So we have this cycle here, which proves this direction of the proof. All right, now we need to prove the other direction. So now we need to prove, right, the converse of this statement, or the converse of this statement. If E belongs to a cycle, then G1 minus E is connected. So we assume that E belongs to a cycle, and we prove that G1 minus E is connected. Assume E belongs to a cycle. Let's call that cycle, let's call it C. Okay, so because E belongs to the cycle, then we have, let's say, U, then V, and then some other vertices. I'm just going to call them W1, W2, all the way up to WK, and then finally back to U again. All right, so let's say this is our cycle. So essentially you go from U to V to somewhere else. This has to be the case if E belongs to a cycle. We can write that cycle by listing it first, starting at UV. All right, now we need to prove that G1 minus E is connected. So to prove G1 minus E is connected, let A and B be arbitrary vertices in the graph G1, or I guess I should say G1 minus E, but the vertex that's going to be the same. All right, so we start with choosing any two vertices in this component of the graph where we've deleted the edge E, and we need to prove that there's a path connecting them, right? That's what it means for a graph to be connected. So we need to show that there's a path connecting A to B in this component G1 with edge E deleted. Okay, now we know that G1 is connected because it's a component of the original graph. So there is an A to B path in the original component G1. Now, if that path does not contain the edge E, we're done. Right? Because if that path doesn't contain the edge E, then that path is still going to exist in G1 with the edge E deleted. Just take that exact same path. But if that path did contain E, and let me try to draw another little picture here. All right, I'm just going to zoom in here and say this is my graph G1. Here's A to B. And let's say in our original graph G1, there is a path, and within that path it includes the edge E. Right, the edge from U to V. So if that AB path does contain E, then that path is not going to work in G1 minus E because now we've deleted this edge. Right, we've taken this edge away and now this doesn't work as a path anymore. But remember, we started off by assuming that there was a cycle that UV was a part of. In other words, we can continue this sort of over here to form a cycle. And now what we can do is just put together the original part of this path, then follow the cycle to get to V, and then finally continue on that path to get to B. All right, so if our AB path, for instance, looks like, let's let the AB path be A, then we'll call it X1, X2 through Xi. Then we go to U, then V, and then Xi plus 1 all the way to Xk, and finally to B. Oh, let's call that J. We already used K before. All Right, so essentially we're saying from here to here, the first part of this graph is from A to xi. Then we visit u, then we visit v, then continue all the way to here. Well, we can form a new path in G1 minus the edge E by following the original path, then following this cycle that we had learned about earlier, and then finally following the rest of the path to B. Right, so we get the A to B. Now, we have to be careful here. Technically, it's a walk. It might repeat some vertices, but that's okay. We get the A to B walk as follows. A to xi to u, and then instead of going directly to v, we're going to follow our cycle until we get to, I guess we'd have to follow it backwards here, until we get to v. So wk all the way to w1, then to v, right? So now we followed our cycle backwards, we've gotten to here, and now we can continue the walk to get to b. So now we have xi plus 1 all the way to xj, and finally to b. Okay, this is in the graph G1 minus E. I've run out of space here. But because we have an A to B walk, there must be an A to B path. Based on some theorem that we learned in chapter 1. If it has an A to B walk, then it has an A to B path. Therefore, G1 minus E is connected. And so we have proven both sides of this if and only if statement, and we are done with the proof. Great. So now we know from this theorem that an edge of a graph is a bridge if and only if it does not lie on any cycle of the graph. This is a really nice theorem because it allows us to pretty quickly identify what is a bridge and what is not by looking at a graph if we have a picture of it. Now remember, we had said that a tree is just a graph that has no cycles, which means no edge in the entire graph is going to lie on a cycle, which means every single edge of a tree is a bridge. So if you start with a tree graph, you can delete any single edge and you'll be left with a disconnected graph. Okay, and so we get this corollary which says that a connected graph is a tree if and only if every edge of the graph is a bridge. Okay, and in the next video we'll talk about some other corollaries that follow from theorem 2.1.1.